Okay, recording started. Very good. Remember that this is our last but one lecture for what regards my part of the subject. We will have another lecture, as you see on the calendar, on April 19. It will be the last one. And it will be like this one, in presence in Ravenna. If you, Nemran, cannot attend for any reason, let me know, as usual. And then April 19, I will also, at the closure of the lecture, I will give you a summary of what we did together, and I will discuss a little bit the questions that may come out at the exam. The exam, as you know, it's oral, and we will make the exam of May 10 to the next exam together, Professor Katie and me. And the other exams may be that you find only one of us, but it depends on our commitments. For the first one, we will be there together if something goes straight for the next weeks. Okay, perfect. Now, as I anticipated last time, today I want to talk about stability of rock and concrete armor units, and I will work for both I will work not on the PowerPoint, but I will use both the screen directly on the web page of this lecture and the Blackboard. So when I will turn to the Blackboard, I will share the screen, and with the camera, I will point it to the Blackboard. So stability of rock and concrete armor units is an issue that you already discussed, at least in part with Professor Archetti. My lecturing is complementary to that of Professor Archetti. I will introduce a criteria that is physically based, which means that it has some connection with the physical analysis of the stability of these units. It's also the criteria that we discussed today. It's a very classic one for the disciplines of sediment transport in rivers and also in lakes and sea basins. So it's, as I said, a very classical approach, which is largely used. So definitely it's a good addition to your background, because I am sure that probably you already heard about this criteria, but it is something that is frequently mentioned and used. Also, it is frequently used by many softwares. The criteria, as you will see, is physically based, but at the end, as it almost always happens when dealing with sediment transport, at the end, an empirical coefficient, some empirical coefficients will be introduced in order to compensate for the lack of support, of physical support to some of the assumptions. But the physical basis gives an idea of what are the forcings and the mechanisms that regulate the stability of these units. So I will refer to this figure here that you see on the screen, which we may open in another window, which basically provides a scheme, a very conceptual scheme of the problem. So we want to study the stability of the red boulder, of the red, let's say, loose material, because these units are can be classified as loose material because they are not fixed each other, they are not fixed to any structure. They are just put over, in this case, an inclined slope, over a slope in this case, and their stability is regulated only by the friction of between units, which is a stabilizing force, and the friction which is proportional to the self-weight of the unit, and it's also proportional to the friction angle or friction factor. And there are also other forcings, destabilizing or stabilizing forces. So at the end, we studied the equilibrium has an equilibrium between different forces, which can be divided in stabilizing one and the destabilizing ones. So, as I said, the unit is supposed to be placed over a slope. The angle can be also zero, which means the angle beta, which is it's related to the slope, to the inclination of the slope, can be also zero, which means that the surface can be also horizontal. It doesn't change the conceptual approach, but in our case, the sediment is always, the unit is always placed over a tilted slope, so an inclined one. Now, what are the forces acting on this unit? First of all, we have the self-weight, which we call W, capital W, and the self-weight is given by the well-known formula, which gives the self-weight as, let me go over the blackboard, I need to get the pens, here they are, and let me, for a moment, let me share the screen and go to the blackboard. In any case, Shada, the figure is on the web page, so if you want to see it, you can look at, you can open the web page on your PC. Okay, let me see here. Okay, perfect. And let me put on the screen the figure, so I use the same symbols. So we have this inclined slope with the boulder over it. I use a different color because I don't have the brown. And let me indicate here the first force, which is the self-weight, W. So W is given by the product of the specific weight, let's call it for now gamma, and the volume, let's call it V. You don't see the volume in the figure on the screen because the volume is estimated in this way. The volume is given by a coefficient which is called C1. So C1 times D cube. What is D? It is a representative size for the unit, for the boulder, and it is cubed because you know that, for instance, in a cube, the volume is given by the cube of the size of the cube. So it is proportional, the volume, to the cube of a representative size. And the coefficient C1, it's like a shape factor. So it takes into account the shape of the boulder. Okay, so if the boulder is precisely a cube, you know that the shape factor is 1. If it is a sphere, the shape factor depends on, I think it is 1/6 times by pi, something like that. Okay, yeah. Not sure if it is 1/6, but anyway, in any case, you got what I mean. And so at the end of the story, we can express W as the the product of gamma times C1 times D cube. Now, what is gamma? Gamma is, as I said, the specific weight of the boulder, which depends on the specific weight of the boulder material, which we can indicate as gamma S, minus the specific weight of, so let me call this one gamma star, sorry, because I saw that the gamma is used for indicating the specific weight of seawater, so specific weight seawater. Good. And then gamma S is specific weight of boulder material. Boulder material. Now, why do I subtract to gamma S the specific weight of seawater? Because I assume that the boulder is immersed. So this is something I didn't say before. Gamma star is immersed specific weight of the boulder. So it is a conservative assumption. We assume that it's fully immersed. And to give you an idea, gamma S, the order of magnitude usually is about in kilograms force, technical system. It's about 2,500 kilogram force. Okay. Kilogram force means it's if you express it in Newton, it's kilogram force by 10 roughly. Okay. So again, order of magnitude for gamma S is about 2,500 kilogram force. The order of magnitude for the specific weight of salt water is 1024 kilogram forces. I say, sorry? Per meter. Per meter cube, yeah, per meter cube, perfect. Yeah, correct, because kilogram forces per meter cube. And the specific water I said more or less because it depends on the salt content, and usually conventionally we take as an indication a weight of 1024 kilogram force per cubic meter, which corresponds to an average salinity. So if you get seawater with an higher concentration of salt, it's higher. With a lower concentration, is lower. You know that the specific weight of the fresh water is 1,000 kilogram forces per cubic meter. So basically, gamma star is, I forgot a star here. Gamma star is about 1025 kilogram forces per cubic meter. Okay, perfect. So this is the self-weight. Now, the self-weight has two components, which we can decompose it in two components. First of all, let me indicate with beta the angle of the slope. So the specific weight has two components. One is parallel to the slope, and the other one is perpendicular to the slope. Okay, and let's note that beta is also the angle here. You can understand this easily if you think of flattening the slope, bringing beta to 0. If you flatten the slope, also the angle that I indicated last goes to 0. Okay. Perfect. Now the two components. The component of the self-weight that is parallel to the slope is a destabilizing component, while the component that is perpendicular is a component that originates the friction force and therefore is a stabilizing component. Perfect. So let's compute these two components. So the horizontal one, which is called there, there is no symbol. So the horizontal one, let me call it WO, is equal to W sin beta, while W vertical V is equal to W cos beta. It's not very clear on the blackboard. Let me just rewrite it with the black pen. WO equal W sin beta, WV equal W cos beta. Okay, perfect. Now, let's now go on with the description of the other forces. Let's suppose that we get a wave running up the slope. The wave running up the slope is pushing the boulder up with a force. This force is, let's call it F. It's given by, first of all, the shear stress tau, okay, times the surface of the face of the boulder, which is exposed to the run-up. And we can compute the surface as a function of d square, where d is again the representative size of the boulder, times a shape coefficient, another one. The first one was C1, let's call this one C2. Good. Now, now we can write an equilibrium, and the equilibrium at the critical condition. What is the critical condition? The critical condition corresponds to what is called the incipient movement, which means it's a limiting condition where the boulder is still there, but very, very close to moving. So in the critical condition, we have the equality between Fs, let's call Fs the stabilizing forces, and the destabilizing forces. So what is, in this case, what is stabilizing? First of all, we have as a stabilizing force, we have the friction, and therefore the friction is given by the self-weight, which is W cos beta, perpendicular to the slope. So stabilizing is W cos beta times the tan of the friction angle, which is called phi. Let me just write more clearly. So the tangent of the friction angle, this is a stabilizing force, which is equal to the destabilizing forces. Now, the destabilizing force is given by C2 d square tau minus the component, the horizontal component of the self-weight, minus W sin beta. It should be, yeah, it is equivalent to what is written there. And this is critical condition. To identify that the condition is critical, let me put a C close to the tau C, which means critical shear stress. Okay, so now we can write this equation in the form of a ratio. We can write, as it is written on the screen, C2 d squared tau C minus W sin beta divided by W cos beta tan phi, and this is equal to 1. So as you see, it's a physical computation of the equilibrium conditions. Here, I'm making the computation by assuming that the wave is running up. And then you have a wave run down. The wave run down is, on the one end, the velocity, and therefore this shear stress originated by the run down is lower than the corresponding values for the run up. It's clear because the velocity is lower. On the other hand, during the run down, you have equality of the sign, equality of direction for the stabilizing component of the self-weight and the action of the wave. So we will have to study both conditions, what happens during the run up and what happens during the run down, because the boulder can be destabilized in both situations. It can be destabilized during the run up. And then you understand that once that the equilibrium is broken, then the boulder rolls down along the slope. Anyway, the first step is just moving up, but then the equilibrium is broken, the friction force doesn't work anymore, and therefore the boulder rolls down. You understand that to quantify with numbers, this forcing is not easy, so you understand that there must be an empirical component. But let's try to develop a little bit this equation, and by trying to understand, to make an explicit computation for tau c. Okay, so let me write it in this way, like it was written above. Let me write let me write it in this way. C tau c, C2 tau c d square minus W sin beta, or let me bring W sin beta at the right-hand side. Yeah, okay, let me see, yes. It's equal to W sin beta plus W cos beta tan phi. Okay. Now we can write it in this way. Tau c is equal to okay, W, let me just check. W, I think, okay, I can substitute for W the C1 gamma S and gamma D cube. So I think I can write it in this way. W, which multiplies sin beta plus cos beta tan phi. Divided by tau c d squared. Divided by tau c, no, sorry, C2 d squared. Thank you. C2 d squared. Okay. Now, let me write it up here. Tau c is equal to W can be substituted, can be written in this way. So let's try to write it in the form of a ratio. C1 gamma S minus gamma D cube, which multiplies sin beta plus cos beta tan phi divided by C2 d squared. Okay. Now we can write it in this way. First, we can simplify d squared so that the numerator it remains simply a d. And therefore we can write it in this way, tau c, let me write in this form, tau c divided by gamma s minus gamma d. And you will understand why I'm writing it in this way. It's equal to C1 divided by C2, which multiplies sin beta plus cos beta tan phi. Okay, this is the formulation that I want. Is it correct? Okay. Now, one thing, why I wanted to write it in this way, for two reasons. First, you recognize that at the right-hand side, you have a quantity that if you assume that the shape of the boulder is constant, is not changing, if you assume that beta is fixed and that the friction angle is fixed, this is a constant. So this one is constant. Second, this quantity here, if you make a dimensional analysis, is dimensionless. And this is why it's also useful to write it in this way. You can understand that is dimensionless because shear stress is a force divided by surface, and here you have a force divided by a volume multiplied by a length, so it's dimensionless. Very good. So let it write in this way, which is the final expression that I wanted to get to tau c divided by gamma s minus gamma d. It's equal to constant. Okay, this conclusion was reached by Shields in 1936. Shields, 1936. Now, how did Shields reach this conclusion? I'm not sure if you know the so-called pi theorem or Buckingham theorem. And I'm not sure if you already had the background on small-scale models or dimensional analysis. We will discuss it more during the last lecture, probably. I don't think I will have the opportunity to discuss the dimensional analysis today, but the dimensional analysis was largely used in the past in order to find analytical relationship explaining a physical mechanism. And how did it work? It worked in this way. They tried to understand in a physical process what are the variables which are governing the process. So for instance, in fluid mechanics, as we will see, you can identify 9 variables, including the mass density of water, including, in this case, for instance, the specific, the size of the sediments, etc. So, and there are several quantities which you need, physical quantities, which you need to describe, to fully describe the process. So they first tried to understand what are the physical quantities that are influencing the process I am studying. And this is the first step of the dimensional analysis. And you have to put together, without forgetting anything, all the physical quantities. And then the next question is, how many fundamental quantities do I need to describe these quantities? What does it mean? What does it mean, fundamental quantities? It means the quantities that you combine together in order to obtain the so-called derived quantities. For instance, if you think of specific weight is derived from mass density, and volume. And how can we understand how many fundamental quantities are there? It's very simple if you look at the units of the quantities you are interested in. So if you identify 10 quantities governing a physical process, you look at the units, and you know that in physics, basically, you have three fundamental. Let's say, in mechanics, you have three fundamental quantities, three units that combined together describe all the other units, which are length, mass, and time. So in mechanics, which means kinematic and dynamics put together, you can describe any unit of any quantity by combining length, mass, and time. And therefore, the conclusion is that length, mass, and time are three fundamental quantities. And the combination of the fundamental quantities is not unique. You can choose other three quantities. What is unique is the number and the possibility by combining the fundamental quantities to describe the units of any derived quantity. So basically, what Shields did, he identified the physical quantities governing this process, and we will see how many they are. They are 11, just to give you an idea. And then he looked at the units, and the units include only three fundamental quantities. Okay, and then the Buckingham theorem says that if you have a number application of quantities and a number, n, capital N, and a number, lowercase n, of fundamental quantities, okay, then you can describe the whole process with a number, capital N, minus lowercase n of dimensionless numbers. So Shields understood that the process here could be described by a number of dimensionless numbers. So he wanted to identify a dimensionless number, which in this case is unchanged, remains constant, but he wanted to identify a dimensionless number. Why? He wanted to identify why they wanted to work with dimensionless numbers, because they were used to test their theories with experiments in the lab by reducing the scale. So they try to reproduce in the lab in a lower scale what they observed in reality. Now, if you, as we already said, if you reduce the scale in an experiment, it works provided that the dimensionless numbers remain constant. So he understood that a dimensionless number derived in the lab could remain the same number even in the reality. Not Shields understood that, they understood that. Buckingham understood this, and they wanted to work on the dimensionless number because they got the same value in the lab and in the reality. While, for instance, the velocity of the fluid in the lab, it's not maintained because it's a dimensional quantity. So it is given by a length divided by a time velocity. If you change the geometrical size of the boulder, of the slope of the wave, then also the velocity changes. They then tried to study dimensionless numbers. So I want to explain why Shields arrived at this conclusion. He wanted to study something dimensionless, describing the process. And his theoretical conclusion was that this number, which is called the Shields number, this is called Let me write it in red. Sheets number, and then I clean the blackboard, but sheets number. Or sheets parameter is also called sheets parameter. His theoretical conclusion was that the sheets number should remain constant. But Shields understood that the fact that it remains constant, it's an approximation, because it depends on, the friction is not always the same. He understood that the type of movement of the wave in the run-up cannot always remain the same. For instance, he understood here, you see that it's constant independently of the shape of the boulder, and this is not possible. It's clear that if you have a boulder that is square, it offers more resistance than a boulder that is spherical. On the other hand, a boulder that is spherical is less stable. So he understood that this number cannot be independent of, for instance, the geometry of the boulder or hiding condition. So he wanted to study into the lab what happens when you study different conditions. In particular, he was concerned that the velocity of the fluid and the type of fluid movement could introduce a variability in this dimensionless number. So he made some experiment into the lab. And what he did was, let me clean the blackboard. Yeah, thank you. Let's see if we can keep the sketch and keep the conclusion. Okay, so let me also delete this one. Good. So he wanted to study the relationship between, and he plotted it into a graph, between the tau c divided by gamma s minus gamma d and Reynolds star. What is Reynolds star? I think in the fluid mechanics you may have probably studied probably the Reynolds number, which is a number, a dimensionless number, again, which quantifies the level of turbulence. So the higher the Reynolds number, the higher the turbulence of a fluid flow. Turbulence is important because, why it's important? Because they knew, and we know from experiments, that when the flow of a fluid, like for instance the flow of a wave, is laminar, the shear stress is higher than in the presence of turbulence. So basically, Sheets had the same intuition if you wanted to study the dependence of the Sheets number on turbulence, but he used the so-called Reynolds number of sediments. Reynolds number of boulders, which is computed in this way. The Reynolds star is equal to the density rho of seawater multiplied by the what is called the shear velocity multiplied by the diameter, the representative dimension of the boulder divided by the kinematic viscosity of water. And here, so we have the mass density of water. Remember that gamma is given by rho times g. So the specific weight is given by mass density times gravity. And then he had a quantity representing the dimension of the boulder and the kinematic viscosity at the denominator. What is the shear velocity? The shear velocity is can be expressed in this way: U star is equal to the square root of tau divided by rho. Let me just check because I don't want to make mistakes. I'm sure that, okay. Yeah, I made a mistake here, just 1 second, because this is kinematic viscosity, not dynamic viscosity. So the mass density is already included here. Okay, because if you put the denominator, the dynamic viscosity, then you have to put the numerator of the mass density. But here I use the kinematic viscosity, and therefore it's okay. Okay, and this one is correct. This one is correct. So basically, depending on the velocity of the fluid, you have a shear stress. And then if you divide the shear stress by the mass density of water, you get the shear velocity. And the shear velocity gets into the sediment Reynolds number to determine the number itself. And for increasing sediment Reynolds number, you have increasing turbulence, like it occurs for the Reynolds number. Very good. So, what did Shields found? He found that the results of several experiments align with something like this. So there is the curve is for laminar flow, decreasing for increasing Reynolds star, and therefore it means that remember that this number corresponds to critical conditions, which means that if you have sediments above this curve, if you have a size of the sediment that determines a position above this curve, is unstable. This is unstable. This is stable. So for laminar flow, the curve is decreasing up to a minimum, and then as the flow becomes turbulent, the Shields number reaches a constant value, which is varying between in the range 0.047, 0.056. different numbers, because Shields was not the only one making these experiments, and then it was repeated by several researchers, because you understand what is the importance of this intuition and what is the meaning of this. Because my reasoning may be that it has been a bit complicated, that I introduced the reasoning on the dimensional analysis, I introduced these dimensionless numbers, but actually, if you think of our situation, our practical problem, the solution here is very easy, because once that you know, we will make an exercise. Once that you know the velocity of the fluid, and you know how to estimate the shear stress, which is something that we can easily estimate if you remember from fluid mechanics, and we will make an application. You know the specific weight of seawater and the representative size of the boulder, you can easily compute this number. It is very easy. We will make a computation. And then you just have to compare this number with the experimental results. And if you get a number that is from this computation that is lower than a given value from the scar, the boulder is stable. If the number is higher, it's unstable. So they made several experiments because the criteria was very simple to be applied, but of course we need a reference number. And therefore they found results that were more or less in agreement, but with some variability. We will see what may be the reason of the variability. And the important thing to think of is that in the case of groin or breakwaters, we are almost in turbulent conditions. We always have the Reynolds star that is very high. So we don't have to bother about the variability of this curve. We only have to bother about the asymptotic value, which is varying from 0.047, 0.056. I just want to put on the screen the original diagram by Shields. So let me share the screen so that Shada can see it. This is the Shields diagram. It's not easy to be understood. I forgot to say one thing. The diagram is in double logarithmic scale. Okay. So you see this diagram, which contains a band encompassing the results. This was handwritten, of course, with the help of rulers, but it was handwritten. And you see that there is this bar encompassing the results. So even Shields found some variability. And you see here there is 0.05. This is 0.1. And therefore, this is 0.06, this line here. And you see the asymptotic results are between 0.05, 0.06 for Shields. And then later on, other researchers found different values, but just a bit lower. But they were in agreement, basically. So the criteria is very simple, in principle, okay? Of course, now we have the problem of evaluating the shear stress. So the criteria is simple, but we have to evaluate the shear stress. And the shear stress, in the case of groins, we are specifically thinking of groins, but it can be extended to breakwaters. It's caused by two actions, mainly two actions, the effect of waves and the effect of currents. Of course, in some conditions, the effect of currents may be negligible, but we have to consider in principle both. And besides, and then we have other problems, other quantities that, other effects that we have to consider. And considering these effects brings us to correct the Shields limiting number. But let's see, first of all, how to compute the shear stress. And so the screen is shared, just 1 second. Okay, so one thing, Shields worked on flumes in the lab, not on models of groins. He was interested in computing sediment transport in rivers, and therefore he was interested in studying the limiting conditions for materials on the riverbed. It is a similar problem, but it's not the same problem. The main difference is that into a river, you have only one type of river flowing. Of course, it could be bidimensional rather than monodimensional, but you don't have to sum currents, waves, so different type of flows which may superimpose. In the river, you have only one flow. And in the river, you have a slope of the riverbed that is close to zero. You can assume that it's zero. And therefore, because it's very, very low, like 5 over 1, 0.5 over 1,000. I mean, if you think of the Po River is less than 1 over 1,000, the slope. So it's not comparable with a groin. And therefore, the researchers who wanted to apply this method on to study the stability of armor units had to adapt it. Okay, and I am presenting results that were derived by Van Rijn. I think you already heard this name. Van Rijn is a researcher who is currently still working and worked a lot on coastal and harbor engineering recently. One nice thing is that Van Rijn in his website makes almost everything available. So the website of Van Rijn, it's and also Van der Meer, it's they are websites that are extremely useful. So Van Rijn proposed to compute the shear stress just as a simple addition of the shear stress caused by currents and the shear stress caused by waves. And here you see that with tau Cu and tau W, I indicate respectively the shear stress of currents and that of waves. Now, the computation can be done with these two formulas. They are equivalent, but of course, there are empirical coefficients that are to be corrected. So there is 1/2. You can recognize the formula for computing the hydrodynamic forcing in fluid mechanics, which depends on the mass density of water and the square of the velocity and the area exposed to the area doesn't matter because this is stress, it's not forcing. So it depends on the square of the velocity and the mass density. So here you have the 1/2, which multiplies the mass density by the square of the velocity. And the square of the velocity for the first equation of currents and for the second equation of run up or run down. So you can recognize the formula indeed, which is 1/2 rho velocity square to compute the stress, the hydrodynamic stress. Here there is a coefficient which is it is used to adjust the computation. To adjust the computation, these coefficients are empirical coefficients. So what about the U prime? U prime is the velocity of the current. This is an information that we need. So we need, if we have currents acting on these structures, we need to know the velocity, the design velocity of these currents. What about the capital U prime, which is the velocity of seawater particles due to waves? So before braking, as you know, such velocity is small, is given by the near bottom peak orbital velocity of fluid particles, and can be computed according to the linear wave theory with this relationship here. You don't have to remember these relationships by memory, and for sure not this one. Okay, this is something that you probably already studied, but as I said, you don't need to learn it. It's just interesting that we look at the independent variables. So there are significant wave height, HB. Wave height is from crest to through. Water depth, dB. There is the wave period of peak wave spectrum and the corresponding significant wavelength, So let's forget how these variables are defined, because I think you studied it already in wave theories, and anyway, you don't need to remember this equation. After breaking, the velocity of particles can be computed through empirical relationship. We need to distinguish between wave run up and wave run down. There are empirical formula. I'm not sure if Professor Archetti mentioned to you these formulas, empirical formulas for computing the wave run up. These are the subject of also ongoing research, so stay updated. But we just need to know that they are empirical relationship, which can be found in several references that if you look also on the web for a wave run-up velocity, you find several references. And I think I have some references here below, we will see. These FCU and FV are friction factors. Usually you see that FCU, there is another empirical relationship that is given. Let's forget about it. And FW is the wave-related friction factor. Another empirical relationship is here. Okay, so with these two relationship, we can compute the shear stress, these two relationships, and the height of the other empirical relationships that I mentioned to you. Now, in principle, we are done. We compute the shear stress, we compute the Schiltz number, and compare the result with the value 0.056 or 0.047 if we want to be very conservative. Now, let's consider what I anticipated just a few minutes ago. So, some effects, some specific situations which are not considered by the field experiments, by the lab experiments, sorry, are not considered these specific situations by the Schiltz experiments. And in particular, as I said, Schiltz worked in a flume, which was almost horizontal. So first of all, let's wonder what happens if we are in the presence of a significant slope, as it occurs over the side of a groin. We need to correct, of course, the Schiltz factor. And here, even if, you know, we considered in our development the angle beta, as you remember, but when we turned to the limiting value derived by Schiltz, he didn't consider it. So this value, which we assume that is constant, it refers to beta equal to 0. So the experiments by Schiltz and the other subsequent researchers were done with a situation of beta equal to 0. So, of course, Van Rijn, Van der Merwe, who wanted to apply this criteria on the side of a groin, they had, or a side of a backwater, they had the problem of correcting it. So how can we account for slope? Okay, first of all, let's not to forget that a groin can be sloped in two directions. There is the slope of the side of the structure, which is computed along the side, and there might be also a slope in the longitudinal direction, so as a transversal slope and a longitudinal slope. Of course, in most of the cases, the longitudinal slope is negligible, but they wanted to account for both of them. And the proposal was to simply correct, also basing on the theoretical development that we made before, simply correct the critical shear stress through two multiplicative coefficients. One, which takes into account the slope k beta in the longitudinal direction, and one which takes into account the slope beta 1 in the transversal direction. So the proposed relationship for the slope factor in the longitudinal direction is this one, where phi is again the shear angle, the friction angle, sorry, the friction angle. So for down sloping velocity, which means wave run down, the correction factor is this one. We will see with a result, with an exercise, with a practical exercise, that it's fully justified, that to distinguish between run up and run down, it's necessary in these two relationships that we change the sign of the difference between phi and beta. But this is the slope factor in the longitudinal direction. And then the slope factor in the transversal direction is this one. Okay. Now, we will see an application of this because, and also the application will serve to me to, just 1 second, there is something that leaves me with a doubt. So beta is longitudinal and transverse direction, the side of the structure. Okay, because I don't understand. Let's go to the exercise later. I don't understand because here there is a difference, a distinction between run up and run down, and here there is not. And I was expecting the opposite situation. Let's see. Okay, and let me just check. Okay. Now, effect of hiding. Second specific situation that we need to consider. And once again, we will solve this doubt with the exercise, okay? Effect of hiding. This is something that also Shields studied. We are not going into details here. So the effect of hiding is particularly important when you have sediments with different size, because the sediments with lower size get hidden behind the sediments of greater size. And therefore, if you have an assorted mix of sediments, hiding becomes important. And because, of course, the smaller sediments may be more stable, and the larger sediments may be more unstable, because you can easily understand that the larger sediments, basically, they trap the smaller sediments between them. So the smaller sediments become hidden, but if a larger sediment is is staying over a bed of smaller sediments, you understand that the effect of the current, which can move the smaller sediments, may undermine also the stability of the larger sediment. It's not the same stability as the situation where the larger sediment is put over a surface that is not covered by small grains, by sand, for instance. So Shields proposed some criteria, some empirical relationship for correcting the critical value that he found, that he estimated, and the same empirical relationship, similar empirical relationship, can be used also in our case. Actually, there is to say that the effect of hiding, it's not very relevant in our case, because usually the stability, we study the stability of these units, which by definition have a similar size. We don't make a mix. We make a mix only in the nucleus, in the core of groins, but the external part, which is the part that we want to be stable, actually it's made by units with similar size, so it's not very important, and this is why I didn't want to go into the details. And the same thing with the units with particular shape. So if we use tetrapods, for instance, it's clear that the stability of the tetrapods, and in particular some forms of them, some shapes of them, is playing in favor of the stability of each individual boulder. And therefore, also in this case, usually the producer gives empirical formulas for determining the stability. You cannot refer to the Shields diagram directly, but you have to consider the specific situation and the specific features related to stability of the tetrapods that you are using. And for this case, for this specific case, as I said, the reference is given by the manufacturer, by the provider, who often also provide the results of testing. Perfect. Now, for the sake of comparison, I want to mention empirical methods. And empirical methods, which I think you already discussed with Professor Archetti for the case of breakwater. Can you please confirm to me if you already discussed the Hudson formula, which is correct? Perfect. So it is also proposed here. And in order to provide a reference for comparison, I just want to say that a critical issue here is to compute the coefficient KD, because the remaining independent variables are easy to estimate. There is the wave height, a reference wave height, and then there is of course, the mass density of seawater. There is the slope of the structure, but KD it's usually estimated empirically, and here we are summarizing how to estimate it. I just wanted to say that it's in the range between 3 and 10. So we can make an empirical estimation, or we can use a safe value, depending on your design needs. Perfect. Now, let me see one thing. Now I want to check this formula here before we go on with the exercise, because I think that now the best way to understand how these criteria work is to make a simple application, which is available on my website. But before that, I wanted to clarify this doubt that I had here related to the effect of slope. So let's try to see if these references are available on the web. I think so, but let me check, because the references are here. So there is prototype. No, this is one not relevant. I think it is this one, relevant stability design and coastal structure. Let me try with this one, because Van Rijn. Let me try with this one. I think it is more likely to be available. And
There's also a website which says it is online and you don't do that.
Okay, let's see. It's here. Yeah, this is what okay, let me see. Way more, we were talking. Critical shear stress method. This one is shears and stability equation. Okay, let me see. It's not linked, so here. Okay. Okay, this is shields. Very good. Okay. Okay. Here there is some more. Okay, this is the shear stress, the computation. Perfect. The slope effects. Let me see. Okay. Slope factor for a sloping velocity. For longitudinal velocity. Yeah, I think I inverted the two cases. You see here, basically, there is this formula which is found with the difference. The difference is slope factor for upsloping velocity, and okay, here there is, he made also a mistake because this is upsloping and this is downsloping. We will check in the exercise. You see, he made a mistake here because with the sum, it's I would say that it's downsloping. We will see, and with the difference is upsloping. But in this case, it's correct on my website. While this one is longitudinal velocity. So I think I have to change this one here. Let me change it soon. Let me see, in the longitudinal direction. This is in the transversal direction. And in the, yeah, okay. Yeah. Because beta 1 is beta 1. The side and the horizontal plane in the longitudinal and transverse. So beta is longitudinal. So this I have also to invert there. Okay, let me just invert in soon. So you are. Let me see if I remember the password. No. Just one second. Otherwise, I'll make it later. Okay, good. Okay. And then I'm sorry for this. I didn't notice this error before, but it's I updated the web page, and also this year I decided to focus on this part a bit more. In the past, I was more, and also the exercise is correct. So, okay, let me see. I forgot to click here. Stability of rock and concrete armaments. Edit. Okay, good. Okay. So, because this is important. Okay. Side of the structure in the transverse. transverse and longitudinal direction, respectively. Okay, with the following meaning symbols for downsloping show. Okay, the slope factor is the direction equal to, okay, in the longitudinal direction. Now it should be correct. Longitudinal direction equal to, okay, good. Okay, good. Now we can go again there, and then we can get the exercise. First of all, let me, before we check the web page, let's look at the exercise here. And so this is, one second, the text. So let's do like this. Let's open in a new, okay. And let's download the Excel file. Very good. Okay, and then let me check here. Stability of rock and concrete armor units. Now everything should be okay. Let me see. Okay, beta and beta 1 between the sides and the transverse and longitudinal. Okay, with the following meaning of symbol. Transverse direction. Okay. Okay, now we are done here. Perfect. Now let's look at the exercise. It says that a groin with a side slope of 30 degrees is exposed to a significant wave height of 2 meters at its toe. This is needed for the application of the Hudson formula. The wave forcing originates at top wave run-up velocity of 4 meters per second and the top wave run-down velocity of 1.5 meters per second. The value of the wave-related friction factor FW is 0.1, plausible value for large stones, while the density of seawater is 1024 kilograms per cubic meter. It is assumed that the tidal velocity is negligible, so we don't have any current here. The groin is protected with boulders with the characteristic size D 1 meter and a specific mass of 2,500 kilogram forces per cubic meter and a friction angle of 40 degrees. We need to check the stability of the armor units with respect to the run-up and run-down by using the Sheets criteria, by assuming that hiding effects and effects of armor shape are negligible. Verify the stability of the armor unit with the Hudson formula by assuming that NCR is equal to 2. Good. Now, there's an Excel file provided for making the computation, which is here. Let me open it. And at this stage, I propose that we make the break 15 minutes before starting the exercise. Any question?
No, thanks, Prof. We can
Okay.
go for break.
Thank you. Okay, so just before going to the exercise, I just wanted to make a couple of additional considerations regarding the references which I am providing, and in particular regarding the nature of these references. This reference, like my website, these are not reviewed, and therefore I think they are not reviewed, and therefore you may find some mistakes. Like in my website, I inverted the transversal with the longitudinal direction, and here indeed there is a repetition upsloping velocity twice. So this is something that, I mean, it's is to be expected when you refer to sources of information which are not reviewed. Even those who are reviewed sometimes may be erroneous. Just, but consider, my suggestion is consider the reliability of your sources also by evaluating if they are tested or not. So there are sources which are clearly tested because if you refer to, for instance, to a classical book, it's clear that maybe the book underwent under 4 editions and some mistakes, some spelling errors, or some imprecisions have been corrected. But today, this is likely not to be the case, because today we refer to references that are continuously evolving. So it is unlikely at our time that you refer to references that have been published like 50 years ago and then corrected over several editions. Today, it's more frequent the case where we look for the information that is very recent. So, and also information that is available, but especially the requirement that the information is up to date is particularly important. And therefore, when you refer to this recent information, whatever is the nature, it can be a scientific paper, it can be a book, try to check if it was reviewed, and even if it was reviewed, taking into consideration the fact that if a reference is recent, there might be the need to treat the information with attention, with more attention with respect to a well-established reference. And what you have to consider, besides the fact that it has been reviewed or not, is also what kind of review it may have received, how many people are using that reference. So for instance, if you look at Wikipedia, Wikipedia in English is checked by a very large community, it's reviewed by a very large community. So it is generally considered to be a reliable review, a reliable source of information. Also, Wikipedia has the very nice feature that if some people is critical towards an information, they put warning there. But even for Wikipedia, if you refer to the national languages, like Wikipedia in Italian, it is reviewed, still reviewed, but it's reviewed by a much smaller community. And therefore, it is less reliable. This is what I always tell students. If you refer to Wikipedia in English, it's very reliable. In the national languages, you have to be more careful. So the same for information that is not reviewed. It's an information that is widely accessed, or it's an information that is read by a limited number of people. If you look at my web pages, they are read, but not by a large number of people. And another important consideration is the size of the community. If you think of the community of climate science, this is very large. So even a reference like my website, I expect that the climate-related pages are read by a lot of people. The coastal engineering community is very small, and you understand it also if you Google. If you Google something related to climate, if you Google something related to coastal engineering, you see the number of entries is much more limited. So when the size of the community is small, you have to pay more attention. So I'm not expecting that several people are reading the pages, my pages dedicated to Harbour and coastal engineering. Just, I think, maybe 1/10 of the people who read the pages related to climate science. So just consider with care the kind of information that you receive, even if it's from a professor that is an established researcher. And it is something important to be considered. And it came to my mind because I was, on the one hand, a little bit surprised to see, because I gave this lecture already 3 times, I think, but I didn't notice before than today the mistake that I did. While when I prepared this lecture, I made ample reference to the website of Marine, and I noticed that there are several not really mistakes, but several imprecisions that I spotted, like this one here. It's not really a mistake. It's just an imprecision, because of course you understand that he's using the same term. So we just have to understand what is the correct and what is to be replaced, but it's not really a mistake. So just be careful. But by the way, this website is indeed, which I think you already visited. It's indeed very useful. Let's see. It's indeed very useful because you see a lot of information is there: coast and offshore, rivers and estuaries, harbor and channels, training and courses, and most of the information is free. He is an independent consultant. He's not a professor, but he's working a lot on coastal and harbor engineering. So let's go to our exercise then. And here we have, let me see, my website is still open somewhere. Yes, it's here. Perfect. So I can close this. So here we have all the information. So the numbers that you see here are just the data. So the slope of the side of the groin in radiant here, because this is something I didn't say, but you have to be careful in Excel when you use the sin function. The argument, the sin, cosine, the trigonometric function, the argument is to be given in radians. It's very easy to make the conversion, but be careful of that. Also, here we have the significant wave height at the toe of the groin, at the base of the groin. The top wave run up and run down velocity, they are different. You see here that the run down is less than half of the run up velocity. The wave related friction factor, density of seawater, and the characteristic size of the Harbour unit, the specific mass, the friction angle, and the coefficient NCR and critical N of Hudson formula. So here you have the computation basing on the run-up velocity of the shear stress. It's called here tangential tensions. It's an improper translation. Be patient with me. So it's, as you see, 0.5, just 1 second. 0.5, if you look at the formula here, I don't think there is a way to, magnify. No, there is no way. We can do like this. Okay. Here you see that it's 0.5 times B9, which is density of seawater, and B8, which is the friction factor, and the B6, which is the wave run-up velocity squared. So this is what we computed. The formula we apply is similar to that of the website. The same thing for the rundown, with the only difference that we take the rundown velocity, which is okay. And then let me expand it once more, because we can expand here. It's not a large sheet. And then here we have the slope correction factor for the run-up. For the run-up, there is the positive sign. So let me just check if everything is correct here. Equal to, for down sloping and up sloping, yes, the positive sign. So we sum here the friction angle and the slope. And for the rundown, we take the difference again between the friction angle and the slope. And then we can compute the sheet parameter, because the sheet parameter is given by the slope correction factor for the run-up and the tangential tension, the shear stress, and then density of seawater, the characteristic size of the Harbour units, and the specific mass. Just be careful, because be careful of the units. So here in this formula, you see that there is at the numerator, there is the shear stress, I think. Let's see. Yes, the shear stress for the run-up. At the denominator, you have the immersed specific weight, B11 minus B9, gravity, because actually here we use gravity to obtain the specific weight, because here the data reports the density, mass density, and to get the specific weight, you have to multiply by 10, which is gravity. And then, because I have to use newtons here as unit of weight, which is a force, not the kilogram forces, as I used in my explanation of the theory. And then I need to multiply by D, which is the characteristic size, divided by 100, because D is in centimeters, and I need to use meters for ensuring the correctness of the units. And then everything is divided by the correction factor, the slope correction factor. Now, why we divide by the slope correction factor? Keep in mind that the slope correction factor, in this case, we are considering the run-up, should stabilize. The fact that the slope is upward should contribute to stability. I just want to make this consideration because it may look strange to you that we divide by the slope correction factor, because if I go back to the web page, the slope correction factor was a multiplication, but actually here we have to divide, because what we are computing is the critical tau, and therefore I have to divide by the slope correction factor to obtain the correction. And I want just to show you in practice. We expect that we stabilize with the slope upward. It is stabilized, the boulder. So what you obtain, in fact, here is a Shields parameter of 0.038. Now, if I remove the correction factor, I get something higher, which means that indeed, by introducing the correction factor, which is greater than 1 for the run-up, I am decreasing the shield number for my considered boulder, which is perfectly fine, because when computing the Shields number for my boulder, a Shields number that must be lower than 0.056, if there is a stabilization, the result of the Shields number for my boulder should be lower after stabilization. And this is what I obtain here. Without stabilization, because here I removed the correction factor, it's 0.0565. If I put the stabilization, then I get 0.03. You see that I put a check here by using the if function in Excel, which allows me to say if it's stable or not stable. And here the limit for the Shields number is 0.056. You see here 0.056. So indeed, in this computation, if I remove the correction factor, I get something that is just a little bit higher than 0.056, and therefore it says not stable. But in this case, I mean, the fact that it's sloped allows to increase stability. Now, the slope correction factor for the run-up, as you see here, is greater than 1, which is what I am expecting. So it means that it is stabilizing. For the rundown, you see that it's lower than 1. So it is contributing to destabilizing the boulder, which is what I am expecting. And because, you know, for the rundown, the fact that it's sloped downward, the side of the groin contributes to instability. And so this confirms that indeed, when computing the correction factor, for the run-up, I have to sum the two angles, the friction angle and the angle of the slope. For the run-down, I have to take the difference between them. This provides a clear demonstration of the correctness of the approach. This is an empirical way of verifying that a formula is correct. So you may also think at the trigonometric structure of this formula to conclude that you have to use the difference for the rundown and the sum for the run-up. Or otherwise, you empirically can check the result and get convinced that indeed what you need corresponds to what my web page suggests and Van Rijn suggests. Good. Now, indeed, if you now look at the shield parameter for the rundown, which by correction is 0.029, what are we expecting now? First of all, note that here there is no verification of stability, but we could easily make a cut and paste and it would be okay. Just let me check if I put 1 here, it's not stable. I don't understand why. I don't understand why if I change the result here, it's also changing, not stable, the above cell. This is something I don't understand. Let me see. If B20 is, yeah, yeah. Okay, stable was already checking both of them. So if I here put 1, it's checking both of them. It's a double condition. I didn't remember that. I was accurate in making the check. Okay, fine. So let's forget about this. But let me just check. What are we expecting here? If I remove the correction factor, I am expecting a Shields number lower. Let's see if it is correct. That it's indeed lower. And this is what I am expecting, because for the rundown, the fact that it's sloped contributes to instability. You see, from this Shields number without correction factor, I turn to a higher Shields number after correction, which is what I am expecting. Okay, very good. Now let's look at the Hudson formula. It's very simply computed here. And it's significant wave height. Let's see, that somewhere, okay, here, significant wave height at the toe. And then there is the density of seawater that is considered. Let's look at the Hudson formula, just 1 second. Here, so significant wave height, density of seawater, difference density of the boulders, specific weight, better, and specific immersed weight, the beta, the slope, and KD. So here you can recognize all of them: the slope, significant wave height, density of seawater, specific mass of Harbour units, and the two quantities allow me to compute the specific immersed weight. And there must be the gravity here, which is here. And you see that there is also the coefficient KD. The coefficient KD is computed based on the coefficient NCR, critical N, and the angle of the slope. And you see that what we get here is stability. It's quite good stability, like for the sheets formula. So you see that it is comparable. Of course, it is comparable, but let's look at the value of KD. It's quite high. So KD is varying between 2 and 10. So if I put 2 here, it results not stable by a large amount. If it is 5, it's still not stable. If it is 6, still not stable. 7. So it depends on the KD of the Hudson formula. In this case, the number that I adopt for NCR, it's okay. On the other hand, you understand that KD, which also depends on the slope, it's quite high. So it is close to the upper range. You have to consider this. Okay, very good. But all in all, the results are coherent, which is what we are expecting. So to conclude, what is the most indicated approach? First, both of them, the Hudson formula and the Shields theory, both of them are at the end empirical, because the Shields theory has a very good physical basis, which is very good for our understanding. So with such an approach, I look at the figure here, with such an approach, we understand clearly what are the conditions that ensure equilibrium, and therefore we gain a better understanding of the whole process, which is useful because when you get the results, the results, you can better evaluate if you can trust the results or not. So on the one hand, this physical basis, as I said, it's very useful. On the other hand, when we come to the evaluation of the results and we compare our result with the Shields number, we compare the results with an empirical parameter. So there is an empirical correction, and there is also an empirical correction when we work to take into account hiding, slope, etc. So from a technical point of view, let's say that they are two empirical formulations. When you use an empirical formulation, you know that there is uncertainty because the empirical approach is used in order to compensate for uncertainty. So you cannot write a precise analytical model for getting your result, for getting your verification, and therefore you use empirism to compensate for uncertainty. So when it's possible, you use an empirical model, you should make an effort to assess the reliability of the results. There are several ways of doing that. One way is comparing what others have done, like if you are projecting a groin and you are in doubt about the size of the boulders, you look at the groins in the vicinity or solutions that have been used in similar situations. This is a possibility. Another possibility is to compare the results from different approaches and therefore use both of them. And for this reason, I think it is extremely important that you know diversity of solutions, because even in this case, diversity means reliability, means robustness, means a more solid result. And for this reason, I think it's important that you know both of them, and you may also find over the web other empirical formulas. Hudson formula is not the only one. There are other formulas, and Van Rijn also proposed his personal empirical approaches. So it's when it's possible, it's always better to compare. And such a comparison, such knowledge is to be built by a good review of the literature. And at the end of the story, what makes your results more reliable is your good knowledge of the theory of the literature. So these are This is the reason why I also wanted to propose to you this approach, which is, as I said, very classical. Maybe not really in coastal engineering, but it is becoming more and more popular. You see that Van Rijn also considers it in its books. Okay, in his books. Okay, I think for this topic we can. I'm just checking if I said everything. I think we are okay. Most of these references here are available on the web, so I think you have plenty of ways for getting more information. Any question related to this?
No, thank you so much.
Okay, very good. Okay, I think we can now move to the next topic, which is probably going to be, if not the last one, almost the last one. And it is related to dredging in Harbour Basin, siltation and dredging. Okay, let me click over it. And I don't have a PowerPoint, so I will use mainly the web page and then the Blackboard for some steps. Okay, so let me make a premise and let me clear the Blackboard before I move forward, because I want, given that the Blackboard is also visible, partly visible in the video, I want the video to be clear and not be confusing. Okay, before I move forward with this topic, there is one thing that I would like to know from you, and I think next time we may have some time left. Next time, what I want also to do is a recap, as I said. A recap means a summary of what we did and a brief discussion on possible questions at the exam. But still, I think we may have some time. So if you have any wish or any idea for something that we didn't discuss, or we discuss maybe in a simplified way, in a short way, if you have ideas or something that you would like I focus on in maybe the last 2 hours of the lectures, because my prediction is that we may have a couple of hours left. If you have any idea, I would be very pleased to know them. What I need is to know them a bit earlier, because it's very likely that I have to prepare. And so it would be ideal to get, if you have any idea, 1 week earlier. It would be really a lot of fun. If you had a suggestion, something that you are interested in, you would like I expand, this would be really fun and demanding a little bit for me, but also stimulating. So I really would appreciate that. If you don't have any idea, what I was planning to do is something that I never did in the past, which is an introduction, because in 2 hours it's only an introduction to decision theory. Because in Harbour management, the logistic is extremely important. And actually, Harbour logistic is a very specific topic. So usually they focus on the organization of the traffic. So it is a very technical problem, or they focus on packing problems, which means like you have to unload a ship and to pack a truck, how to manage this process, which is exciting on the one hand, but it's not really related to engineering. It's just related to the management of boxes of different size and how to pack these boxes in order to maximize the efficiency of the process, which is not really, I mean, something directly related to engineering. So my plan was to talk about decision theory in a more general way, because packing problems or management of traffic can be considered a very applied case of decision theory. I would prefer to stay with a more general overview, which is, I mean, I think it is interesting. I am used to teach decision theory in my courses related to water resources management and climate change, because also climate change requires actions, and to give priority, to assign priorities to these actions is the problem. Here, I think we can make a similar approach in order to give priorities to solutions in harbor management. But I'm not really sure it is meeting your expectations. So if you have any idea, it's just a couple of hours, so it's not really very relevant. Just let me know. Ideally, if you have any idea, if I get an email by the mid of next week, it would be great. Okay. Or if you have ideas already now, it's even more than, it's even greater. Okay, but let me now introduce the problem of dredging, siltation and dredging. This is another very relevant problem for harbor management. And I want to give you an example. When we decided to activate these programs in offshore engineering and harbor engineering, we had a consultation with the interested parties, and in particular with the Port Authority of Ravenna and with some industrial companies. And therefore, I was interested in knowing what are their problems in harbor engineering. And they said that indeed they have relevant problems in logistics. So they were interested in the logistics of harbors. And they were interested also in something related to the laws in force regarding harbor management. So they wanted experts also in maritime laws and harbor laws. And they said explicitly, we have a huge problem, which is dredging, because we have siltation. It is normal. In every harbor you have siltation. We will see why. We have siltation, and therefore we experience a reduction of the depth of harbor basins, and therefore we need periodically to dredge them, which is fine. I mean, it is something that we are used to do. On the other hand, they have the big problem of the contaminants and how to displace the sediments. And therefore, they said, we are interested in that, even if it is a problem that is interdisciplinary, because there is more treatment theory than hard engineering theory. But this is why I decided also to provide, to give some information about siltation and dredging, why they occur, how we can plan dredging operations, etc. So first of all, why we have siltation in harbor basins? For the very obvious reason that you pass from a higher energetic environment to a less energetic environment. So basically, at the entrance of the harbor, you have a border between an energetic environment and a less energetic environment. So in the energetic environment, which is open sea, you have mobilization of sediments. And so water with sediments gets into the harbor basin for effect of waves or currents. And in the harbor basin, the environment is less energetic, which means less transport capacity, which means sedimentation of a fine material. So this is one first reason. It is obvious. And you have also this natural siltation occurring in natural bays. And it's a process that tends to fill a bay. So when you have a like base in a sea that is highly energetic and where is, of course, availability of sediments, the natural process, the natural way of establishing equilibrium by nature is to fill the base with sediments and transform the coastline into a straight coastline. And it's the same thing that we discussed with the coastal erosion and accretion. If you have a coast with several irregularities that in the presence of a regular forcing, the final result is a very regular coastline. It's a smoothing operation. And there is also another reason for siltation. In the harbors, you have we have operations like loading, unloading, loading fuels, unloading goods, loading goods, and you have operations and you have shipping standing there for a long time. It's not like in the sea where they pass and go. In the harbor, the ships are stopping and therefore they stay there for a long time. So you have releases for accidental releases from the engines, from the tanks of the ships. You may have also during the loading and unloading operations, you may have losses of material, and therefore you have the deposition of these materials that typically are contaminated, are potentially contaminated into the harbor basin. So we have siltation. And here we have a figure that explains what happens. You have currents entering into the harbor. You may have also groins protecting the harbor entrance. And therefore, if you have a flux of sediments, what happens is that in the low energy environment, you have siltation starting from the border of the harbor, because close to the borders you have the lowest energy. You know that the velocity of the fluid, when the fluid gets in contact with a border, the velocity close to the border is close to zero. So this is what happens, and the siltation actually occurs with rates that are impressive. For instance, as you see here, to give an example, volumes of sediments up to 3.5 million of cubic meters per year, which are thickness up to more than 1 meter in 1 year, have been observed in the port of Rotterdam, in a waterway of the port of Rotterdam. So what has an influence on siltation rates? The distance from the open sea, the closeness to, as I said, it's not mentioned here, but the closeness to the borders, it's influential. The area, of course, of the harbor basin, and the area of the entrance in the basin, the tidal range, because these currents in and out are mainly originated by currents, also by waves, but currents are really bringing mass into the harbor basin. The waves are bringing energy. If they don't break, they just bring energy. But the currents bring a flux of water in and out of the basin. The peak tidal current, of course, and the outside concentration of sediments, and the density difference inside and outside the basin. So harbor siltation also depends on the conditions, the natural conditions of water, and we have observed that in brackish conditions or in very salted waters, siltation is much higher, up to a factor of 5 with respect to freshwater conditions. For the higher concentration of sediments and the generation of a stratified flow, because when there is an high density, for instance, of salt in the water, you have a stratified flow, and therefore this causes the increase of sedimentation. And the main issue here, it's one major issue is contamination. Why? Because of the displacement. Of course, if you get sediments that are not contaminated, you can better displace them, you can reuse them. But in the presence of contamination, it's a problem. And it's also impossible to release back the sediments into the sea, because if you have a local displacement of sediments, you have an increase of turbidity, you have damage to the sea ecosystem, a local pollution, which may impact close by touristic activities, close by beaches, and therefore it's a problem. In fact, what in some cases we do is that the dredging ships moves into the open sea and releases the sediments continuously. But this requires, so it's not a point release, but a distributed release, much offshore. This is anyway costly and time demanding, because you understand that it's not an operation that is short in time. So dredging is necessary, because you understand that, for instance, in Rotterdam, with a siltation of 1 meter per year, you have a rapid filling up of the bay if you don't proceed to dredging. On the other hand, it's a demanding operation. So it needs to be planned. It needs to be planned in advance with periodical working, and this planning requires a reliable estimate of the siltation rate that we are expecting. Of course, you can adjust the dredging operations, but it is highly advisable that before building an harbor, building a port, or before expanding the capacity of a port, we predict in advance this planning. We make in advance this planning, because it's something that can be adjusted, but only to a certain extent. You understand that while dredging, also the operation of the port is compromised. And therefore, there is a limit in our capability to dredge and displace the sediments. And we need to understand this limit before planning an expansion, before planning building a new pier, a new port. And it is unlikely that it happens today in the Western world, especially to plan a new port, but it is very often planned, programmed an expansion, even only an expansion of traffic. And given that the siltation and therefore the periodicity of the dredging operations depend also on the traffic, depends on the presence of ships, and given that the traffic is impacted by the dredging operation, before planning an expansion, we need to predict the process. And predicting siltation, predicting a process which is mainly driven by sediment transport is not easy. So how can we then predict sediment dynamics? How can we make a model of sediment dynamics? There are two main avenues, two main modeling avenues. Making a prediction requires a model. The model may be empirical, and it's not discussed here, because we discuss here a kind of more detailed modeling. You may have an empirical model, like, for instance, something that can be applied depending on the behavior of the sediment transport, which we can estimate along coast, across coast, and depending on the behavior on other local behavior of currents, behavior of waves. It is unlikely that you can get an empirical model that allows you also to take into account the effect of traffic, of ship movement, of ships movement. which is not easy to be considered. This is why I am mainly focusing on physical models, which means small-scale models and numerical models. And I want to take this opportunity to discuss the pros and cons of these two approaches, to discuss in more detail. Physical models actually, first of all, let me clarify. Physical models, we use the term physical models to denote laboratory models, small-scale models. So it is something that is used also in the English language. It is used in Italian. So we say modelli fisici and physical models. Actually, physical models, it's a term that may generate confusion because we also use the term physically based model to mean something different. It's an analytical model that is built basing on the laws of physics. And it's called usually physically based model. Physical model is, why we say physical? Because it's something that is physically there. It's not numerically. It's not numerical. It's something that you can touch. It's in the lab. It's a reproduction in small scale of your harbor, of your bay, and therefore it's called a physical model. But actually, probably it would be better to say laboratory model and a numerical model. These two modeling avenues, in some cases, are used together. But in most of the cases, we decide for one or another. And the reason why we make a selection, it's the limited resources, because physical models are very costly, more than numerical models in general. And on the other hand, the numerical models are not very cheap anyway. So it's not something that can be realized with a relatively negligible effort. It's a longer effort in economic terms, but not negligible. Now, the physical model, small-scale model, is nice because it's a reproduction, it's a toy of the reality. And of course, we have to make sure that the physical model is similar to reality. If we want to simulate in the lab, in a small scale, what's going to happen in the reality, or we call the reality also the prototype. If we want to emulate the prototype, we must make sure that the physical model is similar. Similarity doesn't mean only geometric similarity. Geometric similarity is quite clear what we mean. We reduce the length, we reduce the unit of the length, and so we obtain something that it's smaller, but for all the other geometric feature is equivalent to reality, so to the prototype. It's just a smaller reproduction, but all the other geometric features like the ratio between the width and the length of the harbor, so everything that is adimensional, dimensionless, is equivalent to reality. It's clear what it means, but this geometric similarity doesn't ensure that you have also a similarity or equivalence of effects for other physical quantities. For instance, if I want to reproduce in a smaller scale a flow, the velocity is not preserved, and the velocity of the flow in smaller scale is lower. So if you think of a train that moves from Ravenna to Bologna, and you make a reproduction in smaller scale, you understand that if you want to preserve the timing of the train from Ravenna to Bologna, the velocity is not preserved. So you have something that you reduce. If you want the train moving with the same time in a reduced length, velocity is not preserved. So you have to choose. Either you preserve time or you preserve velocity. If we talk just about length and velocity. length, velocity, and time. So you have to choose if you want to, I want to reduce the length, okay, that's fine, but what do you preserve? Time or velocity? Are you interested in what? If you are interested in studying the effect of the velocity of the train over, I don't know what, but over a specific feature, you need to preserve velocity. If you want instead to study the effect of the permanence of a specific train over a certain soil, you need to preserve time. But you understand that sometimes it might be difficult to separate the effect of velocity and the effect of time. In this case, I made a couple of examples that where I hoped to have well separated the two effects, but in some cases it's not easy. And therefore, you understand that you may have some undesired effects, even if you decide, okay, I don't care about velocity, I only want to preserve time. You may have some undesired effect because the same train moving in the same time, but with a different velocity, in what you are interested to study may have anyway an effect. Maybe the main effect is time, but also the velocity. So if you're interested, for instance, on the forcing over the ground, and time is important, so the train must exert the forcing for the same time, but are we sure that the velocity doesn't cause any clear effect on the pressure of soil? For instance, when the train brakes, maybe that there is an effect on soil compaction under the track. So this is just to give you a very simple example that when we discuss about similarity, it's extremely important that we make this discussion, make assessment of the effect of small scale effects or scaling effect, as they are called, or in Italian we say effetti di scala. These scaling effects are carefully considered because in general, I anticipate to you the conclusion. In general, the larger the reduction of the scale of the geometric size, and the more important become scale effects. The more important becomes the approximation, the error that I make. And I anticipate that we will prove that there is only one scale that can reproduce physical processes as they are in the reality. There is only one scale, which is 1 by 1, which means the only scale that allows you to reproduce the reality in the lab is the same scale as the reality, which means that if you want to make an experiment, the best thing to do it is to do it in the reality you are working on. And this is why I often say, look around, look at what happens around, because there is no reproduction in the lab that is as reliable as the reality. But of course, sometimes we need to study the reality under modified conditions after the project, after the realization of the project. And then I am forced to make experiments into the lab. And in fact, there are many labs in Europe and also a couple of labs in Italy, which makes coastal experiments in the lab. So let's try to inspect some more. What are the conditions that we need to satisfy in order to ensure similarity? There is an ample literature and on small scale models, an ample literature which describe what are the solutions for reproducing in smaller scale the processes we are interested in as reliably as possible. Keep in mind that the model very often has a side purpose, and the side purpose is to convince the stakeholders of a solution. to provide a clear demonstration of the impact of a solution. And this is not a technical purpose, it's a communication purpose. It occurs quite often. So very often the reason why we choose a lab model instead of a numerical model is a reason of communication. Because it's clearly more convincing if you bring people into a lab and you show what will happen. They can see with their eyes. If you show a graph over the screen or a simulation over the screen, it is for sure less convincing, even if it's a virtual reality that is excellent, something that is really looking similar. On the other hand, if it is on the screen, if it is produced by a computer, by an artificial intelligence, sometimes, not sometimes, it's always less convincing. And this is why when we build small-scale models, in many cases, we care of the details. So the small-scale model should look as the reality if you have communication purposes. And this is also an advantage of the solution. And I want to show you a couple of pictures. Let me see if they are here. I don't think so. No, they are not here. So just 1 second. I get them in another lecture. I'll be quick. It's in Italian, but it's still. It's slow, but it will be quick, provided the web works well. Ah, no, it's already here, sorry. Okay, here it is. It's a similar lecture, but I think I have pictures here, yeah. This is a model that has been done. It's been done in the University of Bologna in the 80s, so about 50 years ago. It's a model of the Arno River within Florence, and I explained to you the problem. The problem was that in 1966, as you know, Florence was flooded by a huge flood. And by the way, Florence is still exposed at the same risk. If a similar meteorological situation occurs, Florence is flooded. But on the other hand, they tried to study solutions for improving the river conveyance, which means that with the same river flow, you have lower water levels. This is a solution that it's not so straightforward. First, because it's not easy to increase the river conveyance. It's not just enough that you expand the width or the height of the riverbed. It depends on how the flow is taking place. So it's not really straightforward. And second, if you succeed in increasing the river conveyance, it means that more flow is transported downstream, which means that you are exposing the downstream floodplains to the risk of flood. So you are transferring the risk downstream. So it's always a problematic decision to be taken. And they decided to study solutions with a small-scale model. And the small-scale model, as you can see from here, reproduced the bridges in Florence, and in particular the Ponte Vecchio, the old bridge. The old bridge, which is something that is extremely relevant from a cultural heritage point of view. And you may wonder, what was the need of reproducing the houses over the Ponte Vecchio? It was not needed, because we could just reproduce the structure of the bridge that is in contact with water. There is no need to reproduce the houses, because once that you get water at the level of the bridge, water floods into Florence. But on the other hand, the details were reproduced in order to provide a convincing proof to the stakeholders, to the major, to other stakeholders that were invited to see see the model. And here the model is running in calm conditions, and here is a detail of the Ponte Vecchio. And this reproduction of the Ponte Vecchio is still conserved somewhere in the university, because when they demolished, because this model was quite used, it was in the courtyard of the university, and therefore could not be kept there for a long time. At the end, they removed the model, but they kept this reconstruction of the Ponte Vecchio. And here you see some attempt to simulate a flood. This, I don't remember the name of this bridge, but this is upstream Ponte Vecchio, and there must be also, yeah, here it's a figure of a picture of the Ponte Vecchio under a flood. And the idea here was to check the effect of lowering the aprons. The aprons are the foundation of the bridge, lowering the foundation of the bridge in order to increase the area of these passages for water, which you can call them sluice ways, but it's a passage of water under pressure, basically. And there are other pictures here which are related to a model that we did recently to study the effect on the Reno River of a new bridge that is now already built, because the highway A1 from Bologna to Florence was passing before the new bridge over an old bridge, which is running over the piers that I am indicating with the mouse, several piers into the river. The new bridge has only 2 piers here, and is passing now here. So the question was, what's the effect of the new bridge over the current? Actually, there are no piers into the riverbed. So we predicted that the effect was negligible, but the authority, the national authority for the National Highway Administration wanted the new project to be checked. So this is seen from upstream, old bridge here, new bridge here. And I think there is a figure because we reproduced also the bridges, not only the piers, but I'm not sure I have a picture. Here is a flood passing. No, I don't have a picture here of the model with the piers, with the body of the piers put over there. And we did the reconstruction also of the body of the piers, of the full structure, of the bridge, with the full structure of the bridge, just for convincing purposes. Okay, that's perfect. Let's go back. Now, I introduced the concept of similarity at the beginning of the lecture today, when I said that when I talked about the physical quantities. Let me just put in evidence here the physical quantities which are needed to describe a process. They may be divided into fundamental quantities, for which it is necessary to define the units, and derived quantities. Whose unit of measurements can instead be inferred from the units of the fundamental quantities. So we first of all have to identify which quantities we need, and then identify between the set of quantities, identify the fundamental quantities and the derived quantities. And the fundamental quantities may be selected subjectively. There is not a unique selection. The only requirement is that their number is kept constant, and the units of the other quantities be derived by the units of the fundamental quantities. Okay, now Okay, good. Now, the number and nature of the quantities for which it's necessary to define the unit of measurement, and therefore to be considered as fundamental, is arbitrary, but the quantities might be dimensionally independent. So the number actually is arbitrary in the sense that you can decide the number by selecting the fundamental quantities. So if you limit the number of fundamental quantities because you are only interested in describing a part of the process, so I made the example of the train. So if I want to study the relationship between velocity and time, I just need to know the length, and I just need to know the velocity, and then time can be derived, because time has unit time, and once that I define the length and the velocity, I can also derive the unit of time by dividing length by velocity, and then I obtain time. So the number, it's arbitrary in this sense. Actually, when you define the fundamental quantities, the number, when you define the whole set of quantities, the number of fundamental quantities is automatically implied, but the choice of the fundamental quantities remains arbitrary. So in my example, I decided that the fundamental quantities are length and velocity, but I could have chosen length and time, and through length and time, I can derive velocity. So in our case, when we have a problem, we need to identify what are the fundamental quantities. For instance, I mentioned that my purpose could be to assess the effect on soil compaction, and then I need also to introduce other quantities, which are, for instance, the density of the soil, and maybe the specific weight of the soil. Maybe it depends on the type of problem that I have to consider. So let's focus on classical mechanics. Classical mechanics is governed, as we know, by three fundamental quantities. I'm sorry that I don't have a PowerPoint here, and I prefer to go by selection, which conventionally are length, time, and mass. L, time t, and mass m. Mechanics, fundamental mechanics, is described by three fundamental quantities, and the unit of measurements of length, time, and mass are established by international conventions. However, it is in principle possible to adopt new units for mass, length, and time. This is possible. I mean, I can decide that I know that length is measured in meters. I can decide to use millimeters. It's no problem. And these two units, these new units, we can indicate them as RM, RL, RT, as a result of the above change, like can be millimeters, can be mass, maybe measured in grams, and time in minutes, okay? But if I change the units of mass, length, and time, automatically I need to change the units, for instance, of velocity, and which will become millimeters over minutes. And therefore, the value of velocity will change. And we know that by transforming the units, we also imply a change in the value of the physical quantity. This is precisely what happens when you make a small-scale model. With a small-scale model, actually, you are not changing the unit, you are changing the value. So what was, for instance, 100 meters, in scale of 1/100 becomes 1 meter. But the effect that you obtain in terms of values of the derived quantities is the same as if you didn't scale the measure, but you scaled the unit. So if from meters I pass to centimeters, I cause a change in the value of the length, which is the same that I obtain in a small scale model where I actually change the value of the length. So in the small scale model, indeed, I change the length, I reduce the length. In the reality, I can take a measure in centimeters. I pass to meters, I change the value. So it is, the small scale model operates in the reality the same change in terms of numbers of fundamentals and derived quantity, the same change as I change the units. So it is very similar. So the new unit for the derived quantity, what is the new unit for the derived quantity? For instance, if I have a derived quantity A, what is the new unit? Because this is important for me. So if I make a change in the unit of length, what is the change in velocity? This is very easy, because if I change only the unit of length, if length is reduced by 100, also velocity is reduced by 100. This is very easy, but in general, this is a good question. What about forces? If I change the length of 100 and forces are indeed, let me see if the forces, I don't think forces are influenced by a change of length, but if I change the unit of mass, then a force, how is the unit of force changed? And what is the combination of these changes? What is the result of the combination of these changes? If I reduce the length of 100, then I reduce also the mass. What is the result on the forces? In general, we can say that the change in the measure of the quantity A depends on the change in the measure of the fundamental quantities in a way that for now it's not defined. And I think the result is quite clear. I change the units of mass, length, and time, for instance, by reducing the length of 1/10, by keeping the mass unchanged and reducing the time of 1/100, because I may have the need of making the simulation in a shorter time. So I want to change the time of the simulation. I don't want to make a simulation that lasts for 1 year. I want to make it in 10 minutes. I understand that probably it's not possible, but let's wonder what happens if I decide that RT is 1/100, R length is 1/10, because I have a small lab and I cannot stay in a space that is larger, and the mass is kept unchanged. Okay. For instance, when I make an experiment in the lab, very often I don't want to change water. I don't want to change the specific weight of the liquid. Why? Because water is cheap. So if I don't change the specific weight of water, how are the other forces changed? If I don't want to change the viscosity of water because I want to use water in the lab, how are changing the other quantities? So in general, what we can say is that the change of unit of a derived quantity depends on the change of units of the 3 fundamental quantities in classical mechanics. Okay, that's fine, but what is the nature of this relationship here? Now, through dimensional analysis, again, we can prove this relationship here. So let me just open it. We can say that the change in the unit of the derived quantity can be expressed as a power law depending on the changes of units of the fundamental quantities. So once that you decided the fundamental quantities and the changes in the units of the fundamental quantity, you can write the change in the unit of A in this product of powers, which is very nice because it explains what is the nature of the relationship. You can understand that it is justified. Like, for instance, when you think at velocity, we came to a conclusion which reflects what you see here. Keep in mind that some of the exponent may be zero, and therefore, if, for instance, if time is not is not in the unit of A, the exponent gamma A is zero. It depends on the units of A. If the unit of A includes time, then the exponent may be 1, may be 0, may be different. Now, the question is how to determine these exponents. Okay, let's see. We still have a short time. Now, these exponents are, of course, determined by the functional relationship that relates A to the fundamental quantity. And here there is an example. For instance, and there is a spelling error here, if A was velocity V, which is obtained by dividing length by time, then BA equal 1 and gamma A is -1. Clearly, you look at the relationship that allows you to compute the derived quantity, the quantity A, and through this relationship, you determine the exponents. It is very easy. So if it is very easy, but we would need an example to prove that. If the three exponents are 0, it means that the unit of A does not change, even if the fundamental units are changed. And then we say that A is a dimensionless quantity. It's a dimensionless number. It's a pure number. Conversely, if only alpha and gamma are 0, then we say that A is a geometric quantity. What does this mean? It means that the unit of A includes only length, and A is geometric. When only alpha is equal to 0, so mass is not there, but the unit of A includes length and time, then its A is a kinematic quantity. If the three exponents are different from 0, we have a dynamic or dynamical quantity. So this clarifies and reflects the definition of a geometric problem, of a kinematic problem, and a dynamical problem. We know that geometric variables have only length in their unit. Kinematic variables, kinematic quantities have length and time, and dynamic quantities have length, time, and mass. Perfect. Now, therefore, changes of the measured units of the three fundamental quantities imply rigorously defined changes of the derived quantities. Conversely, a new choice for the units of the derived quantities that are dimensionally independent implies a corresponding change of the units of the fundamental quantity. So if I want to change the unit of velocity, then this implies a change in the units of length and time, corresponding a coherent change of the units of length and time. Now, what is our question? Our question is, I have a fluid mechanic problem, also which include a sediment transport problem. So it's not only fluid mechanics, it's fluid and sediment mechanics. What are the quantities that I need to consider in fluid mechanics and in fluid plus sediment mechanics? And what are the fundamental quantities. Let's start with fluid mechanics. So in fluid mechanics, let's forget about the sediments for now. What are the relevant quantities? And they are, let's say, they are 9, but let me follow the train of thoughts that it's followed here. Mass density of fluid, velocity V, and length L, they are three-dimensional independent quantities. You cannot express the unit of one of them as a function of the other two, so they are dimensionally independent. And in fluid mechanics, they are often assumed as fundamental quantities. So in fluid mechanics, we don't take length, mass, and time usually. We take these three: mass density, velocity, and length. Okay. On the other hand, and this is what I want to focus on, fluid mechanics, in absence of thermodynamic, electromagnetic, and chemical effects, can be expressed fully defined by 9 quantities. Okay, they are length, time, velocity, acceleration of gravity, pressure, mass density of the fluid, dynamic viscosity of the fluid, compressibility, and surface tension. 3 of these quantities are fundamental. And then the Buckingham theorem says that the remaining 6 quantities can be expressed in terms of dimensionless ratios between the fundamental quantities, or 6 pure numbers. They are, and here I conclude for today, these numbers: Reynolds, Froude, Weber, Mach, Euler, Strual. And these numbers, which are dimensionless, must assume the same value in the model and the reality. So let me say once again, in fluid mechanics, we can describe all the processes depending on 9 quantities, and you have to trust me that they are inclusive, these quantities. So depending on this quantity, we can describe any laws in fluid mechanics. And the fundamental quantities are 3, because in mechanics we have 3 fundamental quantities. And it is convenient for the purpose of a clearer description that we adopt as fundamental quantity, we adopt the mass density of the fluid, the velocity of the fluid, and the length of the domain L. Now, this implies, if I made a correct selection of these 3 fundamental quantities, that all the other quantities, the unit of all the other quantities, can be expressed depending on the unit of these 3 fundamental quantities, which means that if I make a ratio between the other quantities and a combination of the fundamental quantities, a proper ratio, a proper combination, I get a dimensionless number, because I can express the unit of the given quantity depending on the unit of the 3 fundamental quantities. So it's clear that if I make a ratio between the units, I get a dimensionless number. And the dimensionless number are 6, because it's the number of the quantities that I need to describe the process minus the number of the fundamental quantities. This is what I have written on the blackboard at the beginning of the lecture. And therefore, I can obtain 6 dimensionless numbers, and which have to be preserved in the model and the reality. And these are these numbers that some of them you know already, the Reynolds number, the Froude number, I think you know what is this number. The other ones are less known. But these are the 6-dimensional numbers that I need to describe fluid mechanics, which have to be preserved. And the similarity in a small-scale model of fluid mechanics is precisely dictated by the need to preserve this dimensionless number. And I anticipate that it's impossible in a small-scale model to preserve both the Reynolds and the fluid number, unless you use a different fluid other than water. I think that we can stop here for today. Any question? Did you study?
No thanks. No thanks, Prof.
Okay, thanks a lot. Let me just close the registration.